Hello everyone. Today I want to give a proof, an intuitive proof, of why we are allowed to say that the gradient gives a normal vector to a curve at a point, or to a surface at a point. Okay, so hopefully you've learned what the gradient is. If you're just to be thorough though, I want to just state that the gradient of some function f, uh, and let's say this is a 3D surface, the gradient of that is the derivative of the function with respect to x, and that's your I component of your vector. And then we do the same but with the other variables, so df dy, or partial f partial y, and that's your j component or your y component, and then partial f partial z with respect to k. So this is the gradient, and you might have been told in a class that this will give you a normal vector on a surface at any point on the curve, right? So you can plug in, let's say, you take all the partials, you make this gradient vector, and you simply say, okay, I want to know at 0, 0, 0. So you would plug in 0, 0, 0, and you would find that normal vector on that surface at that point. And we're told, again, that the gradient does this. But why is that? So we're going to start this proof with just a little thought experiment. Let's take some surface in 3D. Okay, so let's imagine, let's say it goes behind the graph and then it comes forward and then it kind of like this, right? Right, so I'm trying to give like how this thing looks, so I apologize if it's a little messy, but hopefully you can kind of see the curve, right? It's this nice little hill-like surface on the 3D plane, right? And let's just take a contour of one of these levels. So at a specific z value, let's say z equals a, we take a little contour plot, okay? So let's assume it's at this level and it encapsulates this part of the curve, okay? So let's bring it out and let's look down above it and put it on the xy plane. So we're going to project it onto the xy planes. So let's imagine it looks like this, and it's going to be kind of here. Sorry, my drawing is going to get a little messy, but I'm not an artist. As you can see, I am a science major. So we're going to project that surface onto the xy plane, so I'll simply redraw it as such. Okay, so it looks like this. Okay, now this curve is, notice how it has a looping fashion to it. We are able to define this parametrically. If you remember parametric equations, it says that I can call x some function of t, so let's call x f of t, right? All that means is that x equals some crap of t, so it could be sine of t, cosine of t, something like that. And let's also map y to a function of t, but a different, unique function of t. Although I guess it could have the same function, but let's just say a distinct, different function of t that y is equal to. So we can call the overall, this is like a reparameterized kind of function, so to speak, r of t, right, this parametric equation, and we can call it f of t and g of t. Okay, now what I want to do is take what's called the chain rule of this. Okay, so that's all I seek to do. Nothing crazy. So we have this new parametric equation. We also have this thing, and now I want to take the chain rule of it, right? I want to take the chain rule of this overall function that comes here. So let's do that. Let's say f of x xy. And let's just say, okay, that's going to be equal to, and we remember the chain rule, right? If you have, let's say the overall function z, we can go to x and to y, and then we have our overall independent variable t. So we have our dependent variable, two intermediate variables, and then we have that t. Sorry, it kind of looks like a cross. It's not Jesus, I promise. Look, I'll give it a little tail. Okay, maybe that makes it a little better. But anywho, remember the chain rule says we take the partial z partial x. We take the partial x partial t. Okay, then we take partial z partial y. And then partial y partial t. And we said that, okay, now for this, we have to say, okay, so f prime of xy, you know, if we could just take these partials, but because we mapped it to a parameter, right, t, a common parameter of t, we now have to rewrite it as f prime of xy equals, and if we're taking the derivative, dz dx dx dt plus dz dy dy dt. So it's very, there's a lot of stuff to this, but I just want to give you a little recap to see where we're at so far, because I know it's easy to get lost. We have this gradient, we know it gives a normal, that's what we're trying to prove exists, and why it's normal, see the normal properties mathematically. So let's take a contour plot, z equals a, projected on the xy plane, and parameterize this curve that's made into a function of t, where x has some t component and y has some t component. Then we call it a vector function. R of t equals the vector function f of t g of t. So we're then going to take our function, take a derivative of it, and we know that to do that we need to do the chain rule because we parameterized our variables x and y respectively, and now we did the chain rule and we find this to be the product. So let's set this equal to 0, and the reason we're going to do that, if when we set it to 0, is to pull out some properties and see something. If we look at this whole thing here, do you notice anything? Well, you might notice that it is a specific, it kind of looks like a dot product almost. So remember, a dot product is you have something dotted with something, you take the x components, multiply together, and then you add them with the y components, multiply together, then the z components multiply together. But here, the dot product would be these two guys, right? Because dz dx, dz dy, and then we also have dy dt and dy dt. So although I think, sorry, this is wrong. This is dx dt. Sorry, it's not very implicit. That it kind of looks like y, but dx dt is here. So the derivatives with respect to t go with each other, and the derivatives with respect to the function derivatives with respect to each intermediate variable goes together. So let's just clump them together as a dot product of the two. So let's call it dz dx dz dy. Okay. And now it's dotted with dx dt and dy dt. Okay. This is a very beautiful proof, by the way. This is why I'm making this video, just because it's like I've learned this about a couple months ago, and I came across it again, and I was just like, I'm going to make a video where I talk about it, because it is just a wonderful proof. So we have two vectors that have formed from this. And you might notice that this one, you might be looking at it being like, oh, that's the gradient. Don't spoil it for the people that don't know. If you're sitting out there, you crazy people. But notice, we have this vector, okay? And we have this weird vector. The reason that this one's not weird is because we actually know what this vector is right here that I have circled in yellow. And to see it, we need to come up to our vector function. So let's just take a derivative of this and see what we get. Okay? So this is the x component, this is the y component, right? X, y. So if we take a derivative, right, what this is going to be equal to is the partial with x with respect to t, right? Because f of t is a function, or x is a function of f of t, so we're allowed to say this. And then we have our y component, which is just the opposite, dy dt. So what this is saying is you have this weird looking vector that we don't know what it is. And we have this other vector which we do know what it is. It's the derivative of this parametrically defined vector function for x and y of a specific level curve. Okay? So let's establish something, what a dot product tells us. So here's our curve again. Let's just say it looks like that. Let's plot what this looks like on this curve. Okay, and let's say the curve is moving this way. Okay, so it's moving in a counterclockwise direction. Okay, now let's plot, and let's call this guy the orange bit. Let's plot what he looks like. Well, we know the derivative is the slope of a tangent line at a curve at a point. So let's just draw that. So here it would be r of t. Or sorry, r prime of t. I'm actually going to redraw it. I don't want to put it there. I want to put it kind of here. So here's r prime of t. And we know this is the derivative of that vector function. So it's pointing in tangent to where that curve is going at that instantaneous point in time. Okay, so that's this vector taken care of. But what about this guy? Well, to understand what this vector looks like, we have to understand that it's equal, the dot product of these vectors are equal to 0. And we can derive something if we understand what the law of cosines say. We know that cosine of theta between any two vectors is equal to the dot product of those vectors over the magnitude of A times the magnitude of B. So we know that we can derive, the dot product of these two vectors need to be 0, okay? And we know that we can satisfy that with some theta value, because we know if cosine of theta would be like pi over 2 or 3 pi over 2, then the cosine, when we evaluate, it's going to be 0. And if we can do that, we then know the angle between the vectors. So how we find theta is we say, okay, theta, and hopefully you've seen this before, is the inverse cosine of A dot B over their magnitudes. I'm just going to write magnitudes because I'm lazy. The magnitudes of A times B. So for theta to be 0, we know that the dot product, because the denominator can't really be 0 or else it would be undefined, right? And you can't really have magnitudes of vectors be 0 unless you just don't have a vector, really. That would be kind of weird to think about. But we know that for theta to be 0, the dot product needs to be 0. So the angle between these, or sorry, not for theta to be 0, for theta to be pi over 2, the dot product needs to be 0. And we know that the dot product is 0. So that means that the angle must be pi over 2. So what does this mean? That means that the angle between these vectors, r prime of t and this weird vector dz dt dz dy, are orthogonal to each other or perpendicular to each other, right? Because that angle is pi over 2. So let's go ahead and graph what this is. So I'll draw it in pink for this guy, but if this is our point, this weird vector, which I'm not going to give a name yet because the suspense, the punchline of this video is giving it a name, is going to run like this. And we know that it has orthogonality to it. It has a 90-degree angle between it. So we call this vector, surprisingly and most amazingly, the gradient of f. Look at that. Isn't that beautiful? All that work just to understand that the gradient is a normal to a surface at a point. And we want to extrapolate this to 3D because if you notice, we're still talking about 2D here. This is on the XY plane. I'm not going to even attempt to draw that, but there's an XY plane here. It's only a 2D thing. So this is the gradient of f for a contour plot in 2D, but it extends to 3D. You're just allowed to do that. You can bring it a dimension higher, and it still works fine. You could even bring it to 4D. I think that would work. That would be really cool. Somebody do that. But yeah, and it holds true. The gradient of when you take the gradient of f, you don't get a value. You get a function where you can plug in x, y, z values and get out a normal. So the way that we use the gradient is if we have some crazy complex curve, right? And we have a tangent. Let's say the tangent says, okay, I'm going this way. Well, we know that a normal, right? If this is a parametrically defined line, then we can say, okay, the normal is coming right out of the surface, or it'd probably be more, because there's some curvature here, it'd probably be more like this, right? And that's what the gradient is doing, and it's absolutely beautiful. So hopefully this proof was a little helpful to intuitively follow. Let me just zoom out here so you can see everything we did. Just one big summary. The gradient of f gives us a normal at any point on a curve. Why is this so? Let's take a contour plot where z equals a constant a, projected onto the xy plane. Define x and y parametrically in a vector function fashion. And let's just take the derivative of that, seeing that the derivative of this parametrically defined function is dx dt dy dt. And now let's take our function and let's do the chain rule on it because x and y are now mapped to a function of t. And when we do that, we get dz dx, dx dt plus dz dy, dy dt, it's equal to 0. And it looks like a dot product, so let's rewrite it as a dot product. And we know that that dot product can be 0. And we know that because of the law of cosines, theta is pi over 2 when the dot product is 0. And because the dot product is 0, there is orthogonality between the gradient vector and this tangent vector. So thus we can say that the gradient gives you a normal to a surface at a point on that surface at any time. So hopefully you guys enjoyed this proof. If you did, please drop a like, comment, and subscribe. I would greatly appreciate it. Hope that you have a wonderful day. Bye-bye.